when it comes to climate, if they are telling you that we've got 12 years left, if they're telling you that we have to ban fossil fuels, what you know is they're either misinformed, they haven't taken the time to understand the policies that they're asking you to accept, or number two, they do understand it and they are part of something even more nefarious that I'll talk about in another video. One of those two things. Cannot produce crude oil artificially. What Mother Nature is doing under our feet in the earth to produce this compound, we cannot reproduce. What that means is if it's gone, our society is going to change tremendously. We may want to rethink the policies that are being presented to us that we're being asked to support. It's not like an extinction event for humans. We've never seen a magnetic pole reversal in a technological society. As a geologist, Antarctica now is covered in ice, but it used to be a very warm, arid, forested continent. And the ice has been there about 20,000 years. Well, now that the ice is thinning from global warming, the satellites are showing, surprisingly, very complex structures under that ice. They're human or intentionally made. We don't know who made them. So these aren't little, log huts. I mean, these are vast architectural complexes. And the assumption is that who or whatever left those there, left them there before 20,000 years ago when the ice accumulated. And there's a good possibility that their technology would be intact in those, or at least some evidence of that technology would be intact. So, John, I think we're at this really critical threshold. All these changes are being proposed in the world. We are looking at creating an Earth very different than what we have right now. When the evidence comes to light, when the disclosure happens, when the evidence from Antarctica, it will come to light, when the evidence shows that the climate that's being proposed is not good for us. The bottom line, I think, for society is it just blows the narrative of the world and our place in the world that we've been led to believe. And I've been thinking a lot about this. How is that received? How are we really conditioned psychologically to all of a sudden? I mean, this isn't a gradual. I mean, this is going to happen pretty quickly. How is society going to deal with that? And how do we embrace that new story in a healthy way? And I think one of the things it's going to do, John, is it's going to tear down the them and us scenario that we have been conditioned, whether it's Earth or off planet, whether it's politically, economically. I think a lot of these barriers are going to have to fall as we come to terms with the deep truth of who we are and our relationship to the world. And so our conversation about carbon dioxide, Antarctica, disclosure, all of that, I think those are all feeding into whatever's going to happen with that new story.
You make an interesting point, and that is that in fact that this could be some kind of an adhesive process that brings together and glues together humanity in the face of all this new kinds of things. The alternate track to that, of course, is that there is a split, and there is one segment that just goes, and backs up in fear and drives them off into the other direction. And the other segment kind of embraces and goes forward and is ready for all of this. And so there are two kind of interesting scenarios in there. I hadn't thought much about the fact that it could really be the thing that binds together a whole lot of people in the culture, in the civilizations around these new kinds of things. But it's going to, if it happens, it is going to be, or when it happens, I guess, it's going to be extraordinary. It has the potential. I've followed this for decades, and people have, disparaged me and laughed at me and said, and I've had to be kind of cryptic about talk. You don't go through the middle of the Pentagon, by the way, and tell them that the aliens are all going to show up and it's going to blow up the world or anything like that. So, but the downstream implications of building a compatible and integrated kind of relationship with a society that was a million years old is just wild and crazy, and it's beyond our kind of ability to effectively think about, really think about how that all might work, because it would essentially blow up all of the underpinnings of how we built our understanding, our paradigm of how this all works.
Yeah, well, and I think that's we've talked about this in our quartet program. I believe as a species, we are and civilization, we're at a very vulnerable place right now. We've opened the doors to the technology. We can engineer nature. And what's so interesting to me, John, is we can edit genes and DNA in vitro right now. We understand the Higgs boson and the Higgs field and the underlying nature of reality. All of that, we still have yet to come to terms with who we are and our origin. And the old story is falling apart so quickly. Darwin's idea of evolution, the evidence simply doesn't support it. A lot of the college professors that have been teaching it know that what they're teaching is wrong. They don't want to mess with the change, so they're retiring. Now we've got new professors coming up through the ranks that are saying we can't teach this anymore. So
and Greg, the same thing is happening with Einsteinian physics, in that there are, the electric universe guys will just convince you for sure. I mean, if you're smart enough to follow them, that Einstein was wrong, and that it's not about magnet, it's not about gravity from mass, it's gravity from magnetism, and so on. And so there's just really big structural kind of fissures within all of this.
Well, there is, and I think what it has the potential to bring us together with a new story that is that reflects the evidence, is based on and so inclusive of so many cultures and traditions that feel excluded today. I think we have that potential, and I think it's going to happen pretty quickly. But then I keep going back, and I'm looking at the World Economic Forum just finished their meetings. They published their notes about what they see happening in the world that used to not concern me at all, until they signed a formalized agreement with the United Nations that the UN would work to implement their vision through the Sustainable Development Goals. And now we're seeing the UN is trying to do essentially, or the proposal is to do what corporations do, to have lobbyists, to have UN lobbyists lobbying for reductions in CO2, lobbying for reductions in the temperature and health initiatives and things, lobbying Congress of the United States, and that's different than what we've ever had in the past. So we've got that going on. At the same time, we've got all the evidence telling us we're not what we've been told, and we're much more than we've been led to believe. And all of those are converging. They're all coming together at the same time right now. On the one hand, the other hand, we've got a generation of young people who are conditioned to disengage from any of this.
Colored by extraterrestrial life and ideas and understandings. I mean, it's just amazing time.
It is, John. It's hard to have the conversation, as you say, without being ridiculed. You were in the Pentagon. I wasn't. I was working in the defense industry in the 80s during the Cold War. And among our cubicles, we didn't have full offices. We had, government cubicles. We would have these conversations, but you couldn't have them, within earshot of your supervisors or anybody else, because everybody thought it was crazy. But again, you look at the from an unbiased perspective, just take the facts. If we were to achieve all of the climate goals that are being proposed by the WEF, implemented through the UN, and now big tech is on board with this, it puts us right smack into the Pleistocene epoch is what it's called. It's not the era, it's the Pleistocene epoch. Why is that important? It happens to be when the first humans emerged on Earth about 200,000 years ago. It puts us into the temperature range of a much cooler planet, not ice age necessarily, but a cooler planet, lower CO2 levels, life much less abundant right now. And then when you look at the indigenous traditions, almost, well, I have not studied every indigenous tradition in the world. Every indigenous tradition in the world I've ever studied, every one down to the T, John, every one of them says we are the product of a greater cosmic community. Not one of them says anything about us evolving slowly, gradually over long periods of time, more primitive forms of life. And they say these things independently. So when you look at the stories, you look at the Sumerian history, you look at the Egyptian history, the Aboriginal history, from the Andean cosmology, we emerge during this time, and those that are responsible for our emergence, they say, come back. And they come back at the end of this great cycle. Well, the end of the great cycle, the Mesoamerican end was 2012. That was the big deal about 2012. But there's a buffer. It's an 18-year buffer on either side, and that 18-year buffer ends in the year 2030, when so many of these narratives and initiatives are the goals are for them to be achieved at the same time. Also, now this is another vector coming in. We talk about natural phenomenon. Our lives are deeply interconnected with the magnetic fields of the Earth and of the sun. They're related. Magnetic field affects every blade of grass, every form of life, every CEO of every corporation, every leader of every nation. And our magnetic field is a mysterious phenomenon. It's believed to be driven by the motion of the core inside the Earth relative. It's spinning independent of the inner core, spinning independent of the outer core is spinning independent of the mantle, and the mantle independent of the crust. The scientific community released a report saying it looks like our inner core has either slowed to an
I saw that. Yeah.
imperceptible rotation, or it may have stopped altogether, which we know it's done in the past. And when that happens, it is a precursor to a magnetic pole reversal. And that is not necessarily, it's not like an extinction event for humans, but we've never, to the best of my knowledge, we've never seen a magnetic pole reversal in a technological society where everything is based upon the assumption that the magnetic field is static, that it's going to continue as it has. So all of our communications, all of our computers, the power grids that provide the heat and light and electricity and pump our water and agriculture. I mean, everything. The memory on our hard drive is linked to the magnetic field of the planet. The memory on our flash drives. If we lost that field for a period of time, which our ancestors say has happened in the past, then we would lose so much of the information at the time we stopped writing it. We would have our written material, but we'd lose a lot of that digital information. And if all of that is happening at the same time these other things are happening, it would set the stage for a reset on a level we've never even considered before.
Yeah, that's a marvelous and important point that you make, because in all of our conversations, even over the quartet, we have really not talked about the magnetic pole shift, and we really need to do that, because it is, if you will, the most inevitable thing, and the indicators are all over the place, and the implications are huge, because all of life, as you suggest, kind of dances to the song, to the tune of whatever the magnetism is. And so let me tell you, that could be the big catalytic event that kind of grabbed everybody's brain and their head and told them, wait a second, we don't need to do this anymore.
It could be. John, when I was a geologist back in the industry back in late 70s, early 80s, my job was to look at the magnetic field of the Earth and see what's happening. And I could see it was very, that's no secret. It was clear that we've been in decline, that the magnetic fields of the
Oh
earth
yeah.
peaked about 2,000 years ago, interestingly, and it has been in constant decline. The last flip, where north becomes south, south becomes north, happened about 780,000 years ago. And what's interesting, it does not appear to happen like clockwork on a regular basis. However, the time between the last one and where we are now exceeds times that we've seen. That usually happens more frequently. So when I began looking at this, what it looks like, John, and I want to say this to everybody listening, I don't think it's going to happen this week or next week. And I don't want people, of all the things going on in the world, I don't want people to obsess and freak out over this, because what has to happen, and at least in the past, is that the magnetic field of the earth has to reach a certain threshold drop. And from that threshold, what happens is it's like the bottom falls out and it just goes into free fall very quickly. Yeah. We are nowhere near that threshold right now. Now, what could trigger that? Something that hits the earth like a ringing it like a bell. You know, if we had a meteorite hit, if we had nuclear simultaneous nuclear detonations, that might do it. Solar flares can do something like that. So, but I just want people to know right now, I'm looking at it. It's, you know, it's not at the top of my list, you know, of my concerns. And if it does happen, it's pretty tough to prepare for that anyway, other than be the best version of yourself. So we have not reached that threshold where it just falls so quickly, it goes into free fall. But I'm just looking, all of these parameters coming together make for a very, very different Earth. And so if who or what is responsible for us, if they're coming back, it's not like aliens, John. They're not aliens. If we are the product of them, they are us coming back. Yeah. And I'm concerned that it'll be positioned from a place of fear.
Yeah, of course. You know,
whatever we find in the ships in the ice in Antarctica, for example, or the technology that's there, or, you know, from another world, it's always being positioned with animosity from a place of fear.
I know.
And I think that maybe these discoveries are going to help us change that thinking, and maybe they are us. And I think it's really important we look at this with an open mind, not from a place of fear, because these are natural phenomenon. Because one of the beautiful things that could come from a pole reversal is that our memories, the memories of our hurt and of our suffering, and of our differences and the wars that have happened in the past, those memories would be vulnerable to those magnetic fields. And it's very possible that we could come out on the other side with a very, very different
maybe that's the reset of the AI or something like that.
Well, if we're in a simulation, and again, we've had that conversation. I mean, we're all over the map on this conversation, but but if as the evidence suggests that we are living a virtual reality, a simulation, as a computer scientist, what I have to say is that even a massive on a massive scale, there would be limitations of how much data can the simulation hold, and is it on a timer? So, you know, do we go out and look in the sky and do we see in the clouds it says time out? You know, or you know, do we time out? And we don't know the answer to these things. But if we look at all of these things coming together, why 2030? Why Earth? Why are we trying to change our the geophysical parameters of climate and temperature to go back to the time when we originated on this planet? And scientists are in agreement with that. They say, yeah, we showed up 200,000 years ago. They just don't know how. They're not in agreement on how it happened. And maybe this is the conditions for, maybe they are more optimum conditions and for us when we emerge than for the intelligence that is responsible for us being here, that is responsible for the genetic fusions, in human chromosome 2, chromosome number 7, the mutations. that give us our, prefrontal cortex and the complex speech, all of
But
those things all happen right at that time.
well, you got to believe, at least for me, you've got to believe in some overarching grand plan and strategic kind of orientation and direction, and that we're not just floating around here kind of doing our own thing, and that there is this evolutionary process that, by the way, has been tried many, many times. There are other, millions of times literally in other places in this universe, and that there's some kind of direction to this whole thing, and it's not just going to go over and go off the cliff. I mean, there are presumably, reportedly, kind of institutions. I mean, groups, other than human groups, who have a vested interest in the well-being and the development of humanity, and it's their job to kind of seed these kinds of life forms around different kind of places. And so we're not in this alone.
Right.
There's a direction, and it's an intelligent direction. It's been done before. There's a process, and it works in other kind of places. And so there's a lot of reason to have hope. It's just uncertain at this time exactly where that crack of light is going to come through, that's going to show us where to go.
I agree, John. And my highest hope and my greatest prayer would be that whatever is coming for us down the road, whatever we're on the threshold of, that we could approach it with love, peace, cooperation,
Yeah.
cooperation with other forms of life that may have had a role in our existence, or maybe are responsible for our existence. And I think about this a lot. What if we think of that intelligence as essentially our parents, which is what the
Yeah.
indigenous people call them? What would it be like for them to be gone for 200,000 years and come back and see that what they have seeded
Yeah.
has evolved and emerged into the beautiful things that we have evolved into, as well as some of the frightening things, and where we go with that.
Yeah.
So there's so many possibilities, but what we know is that this is not business as usual, and
Yeah.
that what we're experiencing now is not sustainable in the long term. Something's going to give, and I think part of that giving, what's going to give, is our ignorance of our relationship to ourselves and to our
Yeah.
past. And as we emerge with a new human story, that changes the
Yeah.
context,
Yeah.
and then the changes begin to make more sense. The changes make no
Yeah.
sense because we are led to believe a story that is so far removed from the deep truth of who we are. So it's
I,
an interesting conversation, John. I
I
appreciate you
I
having it with
agree.
me.
Yeah, that opportunity. You need to really think about all of this stuff. It's just opportunities, and figure out what the opportunity is to go forward and learn, and send, or whatever the terminology you want to use, because that's the kind of essential. The whole idea is about expanded awareness, right? How do you within each step of how this goes, open your aperture to be able to see life and see yourself in a larger, in a more sophisticated and kind of way. And so each one of these seeming disruptions are but opportunities to allow us to kind of see ourselves differently. So it's a fascinating time.
So let's take a look and answer some of the basic questions. And in that way, you will be empowered with a deeper understanding of what it is that you're being asked to change, what it is that you're being asked to give up, and what it is you're being asked to give away. The bottom line for me is the people that can least afford the magnitude of change that we are being asked to make, the people that can least afford it, are the ones that are going to suffer the most. And once again, these are people that have the least bandwidth to absorb the kinds of changes. Many of them live in nations. Many of them live in communities that are inundated with poverty. And if you don't have resources that you can fall back on when these kinds of policies are being initiated, when the laws are being created, this is where the suffering comes from. And in my opinion, it's unnecessary. I think There are technological answers to move through these transitions in a healthy way. And once again, the renewables that are being pushed cannot be the answer. We've done an entire video on why that is, and how much oil, how much hydrocarbon, and the rare earth minerals that are finite in nature, how much of that it takes to create what we call renewables. I don't want to be redundant here. I want you to know that I have addressed all of those things. They are in the videos listed down below about the dirty secret of green energy and why it cannot and is not the answer to what we're looking for as clean baseload energy. I talk about other forms that are available. I'm going to talk about one of those now, reiterate it here. So let's just jump right into this. Let's find out why the crude oil that comes from our earth is so important to us in our lives right now, why we may want to rethink the policies that are being presented to us that we're being asked to support as we move into this 21st century. So when we talk about the role of crude oil and fossil fuels in our society and in our world today, we've got to be honest about what's happening, or how can we possibly solve the problems if we're not honest about the problems? So I'm going to bridge this conversation, the beginning of this conversation, with the way that we ended a previous video on the role of energy in our country and in our world today. Right now, the energy that is consumed in the United States of America, about 89% comes from fossil fuels, 11% from renewables. And of those renewables, what you're seeing is only about 9% is solar. The other 22% hydroelectric, 24% wind, and you can see what's 2% geothermal. You can see what's happening here. I think the renewables are great where they make sense. We live in such a huge geographically diverse nation with such geographically diverse climate that these parameters simply do not make sense for our entire nation. We can't count on them for a reliable baseload energy. They're good to supplement with. For now, they aren't going to last because the technology that is required to produce the green energy, what we call renewable energy, is not sustainable. The 17 rare earth elements that are in finite deposits in just a couple of nations of the world, Russia, China, primarily, a little bit in Australia. Again, we talked about these in previous videos, simply are not sustainable in the long term. So of the 89% of the fossil fuels, petroleum makes up 37%, natural gas 32%. They are coming from oil. And we're being asked to let this go with nothing to replace it right now, nothing viable, nothing sustainable. And it makes absolutely no sense to do this whatsoever. So it all begins with crude oil. And what I found in the in the conversations, that many people in our community really don't know what crude oil is. They don't know where it comes from. There's controversy about where it comes from, and I wanted to address all this. So let's start at the very beginning. Crude oil, it is a mixture. It's simply carbon atoms that bond with hydrogen atoms, and they form what are called hydrocarbon molecules. A very simple one is methane gas. A methane molecule looks like what you're seeing on the screen right now, CH4, carbon, hydrogen 4. Carbon is the black sphere in the center of the molecule, and then there are 4 white molecules around it. This is the simplest one that is naturally occurring. It occurs within the earth. Butane is one that is more familiar. We use this often for cooking and for lighters and things like that. C4H10, 4 carbons, 10 hydrogens, and you can see it's a little bit more of a complex molecule here. The black spheres are the carbons and the white are the hydrogens. You can count them out. And these are our schematic diagrams, but we know that these are real because recent technology has allowed scientists to actually photograph these. And this is fascinating to me. So what you're seeing in the upper left-hand corner is the schematic of a very complex hydrocarbon molecule. It's called hexabenzochroridine. Upper left-hand corner, you're seeing the schematic. Now you're through the photographs, photomicrographs, you're actually able to see the molecules themselves that are depicted through the schematic. So I want you to see this. This isn't just an abstract concept. I mean, these molecules are really there. This was published in the prestigious journal, peer-reviewed journal Science, September of 2012. So we've known this for quite a while, and we've known how these molecules work. What I really want to emphasize here is here we are in the 21st century, all this high tech that we've got, artificial intelligence and internet and virtual realities and the metaverse and all that. And to this day, we cannot produce crude oil artificially. What Mother Nature is doing under our feet in the earth to produce this compound that is used in over 6,000 facets of everyday life, we cannot reproduce. What that means is if it's gone, our society is going to change tremendously. Now, there is a lot of controversy about where it comes from, how long it will last, and if it will ever be gone. I'm going to address that. But I want to emphasize that it is such a mysterious compound in some respects that to this day, we cannot produce this in the lab. We can't make it artificially. So why is this important? Well, it's because of the way we use it. Crude oil plays a vital role every day in our lives. Some of it is obvious, some of it's not. And this is important because when I'm talking to young people about this, young people come to our live events, and again, they're being taught to demonize anything carbon-based and to hate oil and to fear the oil. When they think of oil, they're thinking of gasoline in the car, and that's it. Or, oil in the engine to make the car run. They have zero clue that every facet of their lives, including the technological facets of all the gadgets they love, could not exist without petroleum products. They have no clue as to that. So, I mean, I'm just giving you a quick example here. Sports products, the tires on bicycles, tires on motorcycles, tires on automobiles, all petroleum based. When it comes to the green renewable energy you're seeing here, like the windmills and the solar panels, it takes a tremendous amount of hydrocarbons, of petroleum-based energy to produce those windmills, to produce the solar panels, to melt the silica that comes from the earth into the form of silica that is required for a solar panel. It doesn't just come out of the earth. For the wires, to create the wires and the batteries, and to remove these products from the earth to even produce cobalt, to produce the different materials we need for batteries. And it all is hydrocarbon based. We don't think about this stuff. Our food, the water that comes out of the earth to irrigate our crops, because so much of the world is in drought right now. It comes from hydrocarbons. And you say, well, you could use solar panels to do that. That's absolutely true. And the solar panels and the aluminum frames or the steel frames that house them, and the wires and the batteries and the concrete pads, all are hydrocarbon intensive to produce. Medicines, cosmetics, look at this. I mean, I'm just listing a few of them here. I want you to see how oil is used, so then you can see why it's so important in these 6,000 products. So what you're seeing on the screen, and one of the mysteries of the way that that oil functions. The orange that you're seeing here, this is where the crude oil, and there are many different kinds of crude oil heavy, crude oil light, crude oil sweet, crude oil sour, all define different properties of the oil itself. But altogether, the composite, when they go into a furnace right here in the orange, here's the interesting thing. As that furnace creates different temperatures, there are different products that are produced from the oil that comes out of the ground. The different temperatures are breaking down the molecules, different temperatures, different pressures. So higher temperatures, when this first goes in, higher temperatures, you're going to get the heavy diesel fuel. By the way, if you ever see any oil refineries, this is why you see the towers. This is what's happening in the towers. So the heavy oil is coming out first, then the temperatures begin to cool a little bit, and you get a little bit lighter oil, lighter diesel, and then you get the kerosenes, then you get the naphtha. And let me just give you a better idea here so you can see the temperatures. So higher temperatures, 1,050 degrees Fahrenheit, residual fuel oil comes out. Now the temperature's cooling down 650 to 1,050, you get heavy gas oil. Then 450 to 650 is diesel and heating oil. 350 to 450, kerosene, jet fuel. 185 to 350, it's the naphtha. 85 to 185 is the gasoline that we're using in our automobile. So look at all the products that come out before it ever gets to the gasoline. And then the cooler temperatures, less than 85 degrees Fahrenheit, is the butane and the lighter products. So this is how the energy that comes from the earth is producing. And by the way, it's taking fossil fuels to to do the heating to produce what it is that's coming from the fossil fuels. So we talk about a barrel of oil, and a lot of people are surprised by this. I know when I was a kid in the Midwest, we used to burn our own trash in our own backyards. Everybody had a 55-gallon barrel that used to be called an oil barrel, 55 gallons, and we would put our trash and we'd burn our trash, daily or weekly in that before it became centralized, before the trash trucks came to pick up your trash and take it to a landfill. And they were 55-gallon drums. So a lot of people are surprised when they learn that one barrel of oil is not 55 gallons. It's 42 US gallons. And there's a reason for that. Back in the 1800s, I'll just give you the history. In the 1800s, the barrels that were used for the early production of oil had been used to hold other things, like fish, for example, in the docks. So they reused those barrels that used to hold fish and other products to ship the oil in the early oil production, the early oil industry. And one of those barrels at 42 gallons would weigh 300 pounds. And that was a nice even number. It was a good weight that could be transported. So they stuck with it. So 42 gallons is a barrel of oil. From those 42 gallons, these numbers aren't going to add up exactly because of rounding, but it gives you a good idea. From a 142-gallon barrel of oil, about 19 gallons is gasoline. All right, so that's the lion's share of what's happening there. Approximately 10 gallons for diesel and heating oil, 4 gallons for jet fuel, almost 2 gallons for heavy fuel oil, a gallon and a half for propane, asphalt, and road oil, just about a gallon. Petrochemical feedstocks that they use for other products, one, and then all the other products, approximately 5, not exactly, but approximately 5. If you add these up, they're not going to add up there to 42. It'll be a little bit more because of the rounding, but it just gives you proportionally what kinds of products are coming out of a barrel of oil. We use a lot of this stuff. I mean, just in cosmetics and personal care alone. Hair colors, mascara, nail polish, lipstick, perfume, most lotions that you're using on your skin, lip balm, toothpaste, deodorant, shaving cream, soap, hearing aids, because of the plastic casing for the hearing aids, again, shampoo, contact lenses, combs, brushes. Now, can we make these from other products? Absolutely. Absolutely we can. However, on the magnitude that they are used globally, it's not possible to use as other products. So, for example, I mean, there are toothpastes. I use toothpaste that has no petroleum in it. It is handcrafted locally. It's, things like baking soda and myrrh, the herb or the mineral myrrh, cinnamon, turmeric, things like that. But it's not produced that way on a commercial basis. Can we make clothing that is not use petroleum products? Absolutely we can, but to do that, so for example, if you're making hemp-based clothing, and again, I live in a small rural community and there are places where that happens. It is a cottage industry. It is not a global industry. And to do that, you've got to grow tremendous amounts of hemp. And to do that, to grow it on a consistent and reliable basis, commercially viable basis, is going to require fossil fuels to do that. Can it be done small, local cottage industries? Yes, it can. Absolutely, it can. But every day we've got over 6,000 daily applications. And I'm just going to read some of these because young people aren't aware that the petroleum products are used in things like medicines, antihistamines, the candles that we rely on. Of course, we can burn candles from other things, but they can't be produced. What would happen if we went to beeswax for all the candles on the planet? What would that do to the bee population? I mean, you just think about things like that. The paints, the capsules that encapsulate so much of the nutrients and the supplements that we take. So battery cases, the way that we are producing antiseptics, insect repellents, fertilizers, guitar strings, antifreeze, eyeglasses, parachutes. One of the things that a lot of young people might think about is computers in general. We could not be having this conversation because the computer or the phone or the iPad you're seeing this on is not possible without petroleum-based products. The casings that house the electronics themselves, the wires, the way the wires are coated, the way the wires are connected together, the components that the wires are connecting together. Sheets, pillows, hand lotions, all these things are using petroleum-based products to make them viable on the global market today. Now, once again, I'm just going to say many of these can be produced in cottage industries on a local level for smaller consumption, not on the global basis that we're producing it right now. So I want to give you some sense. If we had a day with no petroleum products in our lives, I mean, this is just a handful of things. The food in the grocery store that you are so accustomed to seeing, that food is using petroleum-based products for irrigation to bring the water out of the ground. It's using it for harvesting. It's using it for transport. It is using it to get the people into the fields that are doing the harvesting and the transporting. It is using it for the refrigeration or for the heating, whatever it is that needs to be done, for the cooling, for the lighting of the stores where it's being produced. So petroleum plays a very powerful role in our lives. Where does it come from? There's a lot of controversy around this. I'm going to be straight up, very honest with you. The reason is because no one has ever seen petroleum produced in the earth. We have theories. No one living today has seen petroleum produced, so we don't know for sure. And I got to tell you, my geologist colleagues, my science colleagues don't like it when I say that, but it's a true story. We have theories. One of the theories that's been around for a long time, I remember when I was a kid, this is a commercial I always see. Oil comes from dead dinosaurs. And this is a Sinclair oil and gas company. Sinclair gas stations you still see in some parts of the United States with the dinosaur logo. By the way, it's a brontosaurus. It's a green brontosaurus that you're seeing here. Because the thinking used to be that oil comes from what is called a biotic source. That means that the oil, the crude oil, petroleum products are derived from something that used to be alive. And this is what's taught in schools today. It is what I was taught when I was a geologist. There is some evidence to support this. And I think it is probably true for some of the petroleum, some of the crude oil that we see comes from this source. So what you're seeing to the left, you see all kinds of sea life, microscopic sea life, big sea life, dinosaurs, forests, things like that. They die and they're buried, sometimes under the seafloor, sometimes in swamps, sometimes in lakes. They're buried and they begin to decay in a really precise way. And over long periods of time, they are buried deeper and deeper as sediments pile up on top of them. And today we drill down through all of that sediment, through what are called sedimentary rocks. Is usually you find oil, hydrogen, water, and gas in sedimentary rocks because those sedimentary rocks have the pore spaces that can first hold the petroleum products, the crude oil or the gas, but secondly, allow it to communicate so that it can be pulled out of the ground. If they were just in little capsules in the sedimentary rock and the contents didn't migrate from one capsule to another, it wouldn't flow. You couldn't pull it out. Same with groundwater. This is true with groundwater as well. So today, and when I was in school back in the 60s, 70s, 80s, when I was in college, getting my degree, this is what we were taught is the source of crude oil. There's evidence to support it. No one has ever seen it happen. And this is how a lot of oil has been discovered in the last 150 years or so. Geologists looking for the kinds of rock that they know will contain and the kinds of fossils that are indicative of that kind of rock. And the geophysical parameters, faults or no faults, or fault zones or plate tectonics that will support this kind of production. So they will drill down into the deposits and they will pump those deposits. There's a problem with this, however, in that if the crude oil is coming from organic sources, things that used to be alive, the deepest fossils ever found are only about 1.5 miles below sea level, about 8,000 feet below sea level. Those are the deepest fossils. The problem is that oil has been found over 40,000 feet below sea level, 7.5 miles, not 1.5, 7.5 miles below sea level. But there's no fossils that go down that deep. So where does that oil come from? So this is why I went back and I said, I think there's probably some truth to the biotic source of oil. I think that is one way that oil may be produced. There's a new theory now that says that oil is abiotic. I got pushback on one of my YouTube videos. I think it was where I talked about carbon dioxide, and people were adamant that oil is abiotic. Number one, we don't know that for certain. It is a theory. Number two, it's never been proven. There are instances where it's been reproduced, but no one has ever seen it happen again. Now, my personal sense, I think there probably both things are happening. I think there are some sources that are organic, that are biotic, dead dinosaurs. And I think that the new theories, and there are even other theories, regarding meteorites crashing into the earth, compressing certain sediments in a certain way or certain layers. But the abiotic theory, what it says is that the components for crude oil, so the carbon and the hydrogen atoms, are percolating up from deep in the earth, from the mantle. And they are forming what we call hydrocarbons. And these hydrocarbons then seep up into the crust, through the mantle, into the crust, through fissures, or if you want to think of them as faults, preferentially. So there won't be fissures everywhere, but where there are fissures, the pressures from within will push the hydrocarbons into pools that we're finding. And that could be where 40,000 feet into the earth, where those pools come from, because there are no fossils down that low. With that, if there were fossils, it means they would have had to be at sea level at some, or in the surface at some point, and covered and buried to such a degree that they were now pushed down 7 or 8 miles below the surface of the earth. So there are problems. And the bottom line is, I'm going to go back to this. How can we solve the problem if we're not honest about the problems? It's the arrogance of scientists who refuse to allow for new possibilities and new theories is where we get stuck. And this is where, where we have problems when it comes to understanding these things. So I think there is evidence to support this. It has been reproduced the conditions have been reproduced recently, and they're published in peer-reviewed journals. The truth is we don't know. So if the oil is coming from conditions deep in the earth, it would be called abiotic, because it is not formed from dead and decaying forests and dead dinosaurs. So where do we find the concentrations of oil in the world? Or or crude oil in the world? This is really interesting, because when you look at this now geopolitics come into this. You don't see oil coming out of England. You don't see oil coming out of France so much. There's some a little bit in the North Sea that is being produced, primarily gas. Those are big gas fields in the North Sea. You see a lot in Venezuela. You see a lot in Brazil, certainly in the continental United States and Alaska. When we had the energy crisis in the 1970s and oil was shut off from the Middle East coming into the West, the United States went to the reserves that they knew existed in Alaska on the North Slope, far North Slope. It was called Prudhoe Bay. It's still there. And I know this intimately because that was my first project that I was assigned when I was hired out of college without a degree because of my background in computer science and geology to do subsurface mapping on Prudhoe Bay, North Slope, Alaska, so that we could determine the best way to bring that oil to market for the world as well as for the United States. And it was that work that I did in the corporations that gave me the credits that allowed me to finish my degree. I did finish that degree, and it was a little unorthodox because I was actually in the industry and I had my job without the need of the degree because I had an unusual mix of math, physics, and this new science called computer science and programming, along with the earth sciences and geology. So North Slope, Alaska was my first project. But you get a sense for where the oil is, the reserves are located. Now, this, I mean, where it's located in the world, how much is there? This is really interesting. Look at this. The United States tops the world in terms of the reserves of oil. The U.S. holds right now about 264 billion barrels of oil. This is more than Saudi Arabia. Saudi Arabia is where a lot of the oil has come from until recently. New discoveries, new technology now has allowed the U.S. to not only have the greatest number of reserves, up until recently, we were the net exporter. We had enough to be independent from the Middle East here in the United States, and we were exporting products like LNG, liquefied natural gas, to South Korea, to China. We still do, into Europe, to countries that don't have their own reserves. And those products actually burn 50% cleaner than the coal that many of them were using in the past. The LNG, it's still producing CO2 if that's a concern, but it's 50% less, which allowed the U.S. to meet the goals for the reduction in CO2 levels ahead of schedule. Actually, U.S. not only met the goals, but we went beyond the goals and we did ahead of schedule, largely because so much of our electricity was switched from coal into LNG, into natural gas. It's not the answer. I want to be clear. It's a stepping stone. It's a bridge to get to ultimately where we're going. And I want to talk about that as well here. But I just want to give you a sense for where we are with crude oil and hydrocarbons. So based on the current consumption, how long will these reserves last? Well, if we maintain the current level of consumption, the proven reserves right now are equal to about 46.6% of the annual, or 46.6 times the annual consumption. You calculate that in times of years, we've got reserves out to about the year 2062 to 2094, somewhere right around in there. Now, this is assuming that these are finite sources of oil. If the oil is abiotic, if it is coming from something deeper in the earth, that may offset that. But here's the problem. It accumulates over tremendously long periods of time. We're pulling the oil out of the ground faster than even abiotic sources appear to be replenishing the oil. And this is why they say, we've only been using oil since the mid 1800s. Drilling mid to late 1800s is when the oil boom began. We pretty much have pulled it from the easy sources, what they call the low-hanging fruit of retrieving the oil, the shallower, reservoirs, or the ones that flow really easily at a high rate. Pretty much have tapped those. There are probably still some left, and scientists are always finding them. And new technology is giving us ways to even go back into oil fields that were considered depleted with the current technology of the past. Now, new technologies allow deeper recovery, and they're able to pull out more. But the point is, whether it is biotic coming from decayed life or abiotic coming from deep within the earth, not requiring decayed life, the process to create crude oil appears to be so slow that we are pulling it out of the ground faster than it can be replenished. So at the present consumption, adequate reserves through 2062 is when we would start seeing, some problems. What that means is the price will continue to go up because it is harder to pull it out of the ground. It takes more technology, takes more energy. You have to drill deeper into the ocean, drill deeper into the ground, all of those kinds of things. Now, if we were to stop burning crude oil for energy, that would move these dates out tremendously because of so much of the oil is actually being burned. And again, we use it for so many other products, we need to stop burning it precisely for this reason. Do we have other alternatives? Well, I've talked about these. I don't want to be redundant too much here, but I'm going to bridge this with some other concepts. I've talked about this in other YouTube videos on this channel about the dirty secret of clean energy, why solar, why wind is not and cannot be the answer, yet that's what we're being told. And you have seen places where local populations trusted these ideas. They let go of their fossil fuel energy, and now they're sorry that they did. Japan, for example, beautifully after Fukushima and the reactors melted down, they don't have any fossil fuels, and they went back. They rely on imports. Germany tried 100% renewable energy, and they're in trouble now. And they've actually gone back to firing up coal plants to provide electricity for heat and for electricity. And I think it's a powerful testament to what happens when you let go of a sure thing before you have anything to replace it. It makes no sense, and yet that's exactly what we're being asked to do today. So what are some of the alternatives? Electricity. You want to go all to electricity. Well, the problem is that electricity, where's the electricity coming from? What are we using to generate the electricity? I'll just tell you right now, we do not have the infrastructure. We don't have the power grid. We have an aging, dilapidated power grid that is so vulnerable in so many ways that this is not a viable answer. If we go to 100% electric automobiles, then we're in all the problems with the renewables, because all of those automobiles are relying upon 17 rare earth elements. Very few are found here in the United States in commercially viable amounts. They are primarily located in countries that we are not on the best terms with. We can't count on them in the future. Do you want to put your future into unreliable sources of those 17 rare earth elements? They're rare earth because there's not much of them there. When those deposits are gone, we don't know of any other deposits. The way they're being mined right now in some, like Ethiopia, for example, is horrible, with child labor. They have no protective clothing. They're barefoot, wearing t-shirts and shorts, standing in the water, trying to pull out the ore in baskets that they're going to now carry up into the surface and hand over to some adult who's going to take it off to somewhere and ship it up to China to be refined and sold to the world. UNICEF has done reports on this. Amnesty International has done reports on this. It's a very sad story. A lot of people don't want to look at it. How can we solve the problem if we're not honest about the problem? Electricity is not going to be the answer. The renewables aren't going to be the answer. A lot of people wrote to me about hydrogen, and they think, oh, hydrogen is just clean gas. What's the problem with that? Well, let me talk to you about hydrogen. There's not just one hydrogen. There are different kinds of hydrogen. There's what's called gray hydrogen. There's blue hydrogen. There's turquoise hydrogen. There's green hydrogen. The colors are based upon the form of energy that is required to free the hydrogen. Even if it's water, water is H2O. So you've got two hydrogens, one oxygen. You say, okay, you break out hydrogen away from the oxygen, you've got energy. That's true. What energy are you using to free the hydrogen? And now you're back into the same boat. If you're using renewables, you're using a solar panel to do it. I mean, that's cool in the moment that it's working. It's toxic to make. It's fossil and fuel intensive to make. And when the solar panels are no longer viable, they are toxic to dispose of. And now we've got landfills leaching toxic rare earth elements into agriculture, into the groundwater, because somebody didn't think ahead. What do you do with solar panels after they've reached their 25-year lifespan? Nobody really thought about that. And they're showing up in the landfills. They break and the toxins are seeping into the earth. Now, there are places, a few, that are now starting to recycle. It takes time, it takes energy, it takes human intervention, manpower. Somebody's got to be hired to go out, open up that solar panel, pull out those minerals. You got to recognize what they are, and it simply is not happening on the large scale. It's not happening on a viable basis. But look at this. All of the hydrogens, where's the energy coming from? Here you go. Gray hydrogen, the source is methane or coal. That is petrochemicals. Those are hydrocarbons. That is oil-based. Methane or coal for blue hydrogen. It's the same thing. Methane for turquoise hydrogen. Renewable energy for green hydrogen, but it's not really green because you're using fossil fuels to create the green energy to free the hydrogen. So it's a difficult conversation. A lot of people don't want to have it because it does not support the narratives that you and I are being asked to embrace. I'm just being straight up with you. I want you to see where this is going. Do we have alternatives? We do. And I've talked about these, and other people have as well. We have bridging technologies. Now, here's what I mean by this. There is an ultimate source of energy. I believe we will see it in our lifetimes. I'll see it in my lifetime. I'm sure of that. Many of you, I think, are going to see it in your lifetimes as well. I hope you're with us to see it. We're not there today. It is what is called an exotic form of energy. I'll talk about in a moment. To get to that exotic form of energy, we've got things right now. I mean, we could turn the key and start using proven technologies right now. One of those I did an entire video about. It's listed below. It was an element that was discovered during the Manhattan Project in Los Alamos, New Mexico, right up the road from where I am in this studio right now. I'm outside of Santa Fe. Los Alamos is just like right up the road, 20 miles up the road. And there were elements that were discovered that could be used to produce energy. The problem was Manhattan Project was during wartime. It was World War II. And they didn't go with some of the other elements because they needed the byproducts of uranium for the weapons. They needed the plutonium for the nuclear reactors. They needed plutonium for the nuclear weapons that became an entire industry. So there were other elements. And again, I did an entire video on this. I'll encapsulate it here. One of those was element 90. It is still called thorium. Thorium, amazing element, produces zero greenhouse gases. It works in a modified reactor, but it produces zero greenhouse gases. It's inexpensive to produce. It cannot melt down like a Fukushima reactor, can't be weaponized like plutonium in a bomb. It's abundant in the Earth's crust. Most nations have access to thorium, and the waste products can be recycled into the fuel. So this is one example of an element that can be used for what is called base load energy. Base load energy is the stuff, it's always there, no matter what the temperature, no matter if there's wind or no wind, sun, no wind, hot, 140 degrees in Dubai, cold in the Siberia, it makes no difference. It is pumped through the grid. So this is an opportunity for us to upgrade the grids in our nation. I'm in the US or in the world. It is available to us now. It is a proven technology. It's efficient. Take a look at this. 1 ton of thorium produces the energy of 250 tons of uranium. Thorium costs about $1.98 per watt. Coal is $2.30 a watt. So it's even cheaper. Now, this is where the narratives and the wokeness come in, because it has influenced our sources of information and media. And if you do a wiki search or a Google search, you're probably going to come with articles that say this is theoretical. It is an unproven technology. It can't be, because we've already had the thorium generators, thorium reactors that were up and running in the United States, in Germany, in India, in China. And I remember when I was in college, 1970s, we had thorium-based plants in the United States that were shut down in the early 1980s in favor of other forms of energy. So politics came into this. I just want you to know it's not like this pure theoretical idea. It's called a molten salt reactor, MSR. And because it's a molten salt reactor, it works on a different principle than the nuclear reactor. And it's that different principle that makes it impossible. It cannot melt down. The physics won't allow it to melt down. Can't be made into a weapon. I love that. It can't do what Fukushima did. It can't be, used as a weapon against our global family. And I've got really strong feelings about how the elements of Mother Earth are used or weaponized to hurt our brothers and sisters, and especially with the technology we have now. So what I'm saying to you is thorium is a stepping stone. It's not the answer, cannot be the answer forever. We've got something better on the horizon. But thorium is a stepping stone. It's a bridge. So if you took this current energy equation, 89% fossil fuels, 11% renewables, all right, let's keep the renewables, use them where we can to supplement. But if you took that 89%, take away the coal, petroleum, natural gas, and you put thorium in there, clean, sustainable, reliable, zero greenhouse gases, if you're concerned about that. I did a whole video again on CO2. And I'm just going to tell you, if you didn't see that video, we do not want to go to the target levels that are being proposed by the UN and the World Economic Forum. It is a death sentence for our world to do that, for the forests of the world, for the life of the world. And we don't have to guess because we've seen it in the geologic history in the past. You go back, the last time we saw carbon dioxide levels, 180 to 250 parts per million, Pleistocene. We know exactly what happened during the Pleistocene era. It's not good for us. So if it's not good for us, you have to say, who's it good for? That's a whole different conversation. That's another video. So thorium. Thorium is a bridge. It's a stepping stone. A stepping stone to what? Well, to an ultimate form of energy that many of you have heard me and many other people talk about. What we know is that every cubic centimeter, like that little sugar cube you see right there, is about a cubic centimeter. Every cubic centimeter of empty space is not empty. It is teeming with tiny vibratory elements that are called Planck energy, named after the physicist Max Planck. It is called the quantum vacuum. And we have the ability to harness that energy, to harness those vibrations. Tremendous amount of energy. The energy density, 10 to the 93rd grams per cubic centimeter. So in the size of a sugar cube, 10 to the 93rd grams of energy. It's enough to run our nation just from that one for a very long time, just in that one little sugar cube. That could be the base load energy. And smaller units could be maybe what powers our automobiles, or maybe our automobiles are working off the resonance from the energy that's being produced through these technologies. I think we will see this, it's already been proven in the laboratory. It is not commercially viable now. We're not seeing it on a commercial basis. And I think this is where this conversation overlaps into other conversations, like the conversation of disclosure. You all know that disclosure is occurring right now on different levels, not so much on the mainstream level, although that's changing. But the disclosure that we are part of a greater community in our cosmology, that we have had interactions. We have, I mean, they've been recorded for thousands of years by our indigenous ancestors. We've had interactions with advanced intelligence, either from the future of the planet we live in now, so coming back to give us information, or from other worlds that are coming to give us information. And we have derived technology from those sources. And that technology is based on forms of energy that make what we're doing now seem like child's play, that make what we're doing now seem so primitive. And ultimately, we will have access to that, either through the inventions that are already created, or the disclosure when disclosure happens. And I think it will happen on this level. this is the kind of disclosure that will benefit everyone because it will free us from the shackles of limited energy and from the fear of not having that energy, because the energy is abundant, and we have the technology to access that. So everything I'm talking about is a bridge to what I think ultimately will happen. Is it going to happen this week or next week? Probably not. So if we're concerned about petroleum, then the thing to do is stop burning it. It's going to last longer, and allow ourselves to go with a form of baseload energy that is sustainable. It's not going to be susceptible to hurricanes coming up through the Gulf, or to cyclones that would just hit our brothers and sisters in New Zealand. It's not going to be susceptible to extremes in climate and temperature. You don't need the wind. You don't need the sun. Makes tremendous sense. And I want to say to people out there who are in the energy industry, I want to thank you for the work that you've done. And I want you to know that when we develop new forms of energy, doesn't mean that the oil and gas industry goes away. On the contrary, we need to keep producing that oil and gas for the 6,000 plus reasons that I mentioned earlier. The technology, the clean, green, sustainable technologies cannot happen without hydrocarbons right now. That's the world we live in. Maybe that'll change, in years to come. But the world we have right now, I think that the powers that be are not being forthcoming. They're not being honest about what our world looks like if we don't have access to those hydrocarbons, and to lead people into decisions that make it difficult to access those hydrocarbons. It's all about, it's politics, it's fear, it's disingenuous. They don't want to live in that world. So I know behind the scenes, you talk about people, you listen to what they say, and then you look at what they do and how they live. They say one thing, you look behind the scenes, where do they have their money invested? In energy production companies. Their lifestyles are all energy intensive lifestyles. And I know they don't want to lose those things. So nobody does. And this isn't about making anyone wrong. That's an ego-based argument. I think we've outgrown that in our society. We're way beyond that. We're talking about the viability of our planet right now. We don't need to make anyone wrong. Let's share information about what is true and what we have access to, what's possible. And let's move toward that. Buckminster Fuller said this beautifully. He said, if you want to change the world, you'll never do it by fighting against the things you don't like. He said, find a new model that makes the old model obsolete. People will follow the new model. The old model then crumbles away. I'm paraphrasing, because people will use the new model. We find a better way to produce the energy. It doesn't mean that the energy industry collapses. It doesn't mean that people lose their jobs. It doesn't mean that they become obsolete. On the contrary, we need them to continue, and it means that we have taken ourselves, we've matured into a way of thinking about ourselves and our relationship to the world that makes those old ideas of burning something obsolete to produce energy. So this is where I wanted to go with this, replacing fossil fuels with Planck energy from those little Planck scales. We could do this. And we could do it within our lifetimes. The infrastructure it's possible to build this infrastructure relatively quickly. We need the jobs. A lot of people could be put to work. The kind of money we're talking about, if we take a fraction of the defense budget from the United States of America and put it into this kind of energy, and the world would thank us for it. And we could begin doing this in the world as well. So this is the invitation. The invitation. Our ancestors tell us that we're living a dream. You and I are dreaming a dream right now. When we sleep at night, we're in a dream within the dream. I want to show you the science, the false science, and scientists know it's false, and you're going to see that as well. Where is this information coming from? Why do some people believe we have 12 years left? Why do they believe that carbon dioxide levels are causing problems in our lives? I think you're going to be surprised at what you see here. So the question is, where does the UN get the information for the climate projections that our media, that our politicians, that our policymakers are basing their hysteria upon, or basing their impassioned speeches upon, and the platforms that they are running for public office upon. Where's that information come from? Well, they come from models that are made on computers. All right. If you're going to project what's happening in the future, you need a way to take information based upon the past and the present and to weave that into something that can reasonably tell you what you can expect to happen in the future. These are called computer models. Now, I'm probably closer to computer modeling than a lot of people because I did computer modeling when I was in college, Colorado State University. I worked in the remote sensing lab where we used thermal information, optical information, and historical information to build computer models of forests during the Cold War years, so that when our satellites were looking at similar forests, the same kinds of trees, the same elevation, same climate in Russia, for example, or in East Germany, if there were implements of war, if there were tanks or missiles that were hiding in those forests, they would show up as anomalies in the models. So I had the opportunity to work on modeling, certainly nothing anywhere near as sophisticated as what's happening now. So, but I do understand the modeling system. You have to build a mathematic model of the systems to have those projections. So, climate models. When we look at the Earth, the way that climate scientists are building these models, if you look on your screen, there is the Earth, and the entire planet is divided into grids, cubic grid sections, like you're seeing on your screen right now. And every one of those grids has a mathematic formula that represents what's happening in that grid, everything from the ocean and under the ocean to the surface of the ocean, to the humidity, to the temperatures, to the cloud cover, what's called solar radiance, all of those kinds of things. And there are many different models that have been built beginning in 1995. They're called CMIP or CMIP climate models. CMIP is an abbreviation for Coupled Model Intercomparison Project. So we're going to begin looking at charts based on CMIP. So you will see multiple climate models. So they're taking different parameters, and you'll see them all projected onto the same graph and where it is that those parameters are leading us. So here's what I mean by this. When we divide the planet into these into this grid, and each grid has a very precise, and this is both for vertical kinds of information, what are called vertical exchange vectors, between high altitude, low altitude, and all of those things, and horizontal. I mean, wind currents, all of these things are taken into account. And there's a sample, there's a mathematic formula so that mathematically what's happening in that one grid, in that one little piece, is being represented. And then they take all of those mathematic formulas representing all of those grids, and they put them together to create a projection. Now, as you can imagine, this takes a lot of computing power. Some of the biggest computers in the world are using this. So I have no problem with the principle of modeling. Where I do have a problem is that the models are deeply, deeply flawed. The scientific community knows this, and we are so far down the road in this narrative that it's very difficult to push back. It's very difficult to share the truth of what's happening. Scientists, their tenure depends upon this at the university. University funding depends upon this. If you're a researcher, your research has to support these models. There's all kinds of conversation about the levels of corruptness that are happening behind the scenes building these climate models. All right, and let me just show you what's happening. The first assessment report, called FAR, a very innovative acronym. The second assessment report by the UN, SAR. The third, TAR. And the fourth, they changed the notation a little bit, assessment report 4, AR4. what you can see on your screen is that the information in each of those little cells of the grid is becoming more and more refined, or what we say is there's a higher resolution of information. So we're getting better at refining the data, but the principle the data is based upon is what's flawed. So I want you to take a look at this. This is an example of a CMIP. So they are called representative concentration pathways, RCP. What you're seeing on your screen, each of those little squiggly lines is one model that is modeling some aspect of, Earth's climate system, where parameters have been adjusted or shifted or changed one way or another. And you can see that the models are all over the place, but they are generally trending to the top and to the right. So in the future, if you look at the bottom of your screen, the year 2100 is on the right-hand side of the screen. 2080, 2060, 2040, 2020 is where this begins. So they're all over the place, and in general, they are trending up, which is warmer as we go right to our future. So this is an example of IPC climate models of represented concentration pathways, RCP, and you can see they're color coded. The RCP colors in the upper left-hand part of the chart represent the little squiggly lines that you're seeing. Now, the next image that you're going to see is where these predicted models are compared to the actual data. If a model is a good model, here's what should happen. If it's a good model, if it represents all of the parameters accurately, then you should be able to take that model after a moment in time has already occurred. So after the year 2020, for example, has already occurred. And you should be able to go back in, because now we know what the temperatures were, we know what the humidities were, we know what the reflective properties of the clouds were, temperatures in the ocean, we know. So we should be able to plug those in to the model. And the model, if it's a good model, it should tell us exactly what happened, because it's already happened. It should overlay it perfectly. Check this out. This next image is the predicted model versus the actual data. What you're seeing in the black for at this period of time is the actual what actually happened. This is compared to all the predictive models. And what you can see is what actually happened is nowhere near what was predicted in that period of time. Look at it's on the low end of that channel. And the term that's used at these models are actually running hot. All right, hot in terms of literally in terms of temperature. So there was a committee, United States House Committee on Science, Space, and Technology hearing. March 29, 2017 is when this happened. So this is how long ago we knew these models were flawed. And I'm going to share with you one part of the testimony. This is John R. Christie's professor of atmospheric science. So he knows what's going on. Alabama State climatologist, University of Alabama. These next couple of charts are from his testimony in the United States U.S. House Committee on Science, Space, and Technology. Here's what's happening. There's a lot going on here, but you now have enough. I think you're going to be able to see what's going on. The upper part of this graph are the CMIPs. These are all of the climate models. You can see, again, they're all over the place, but they trend warm and into the future. The red line is the average. So they took the average of all of those models and said, okay, some models are high, some are low, but in general, what are they saying? They took that average of 102 of those models, and you can see that red line represents the average of the models. Now, below, what Dr. Christie did was he and his team took real-time data. They used balloons into the atmosphere to sample the atmosphere, to actually sample the atmosphere. They used satellite imagery and satellite information to actually sample real-time what was happening And when they plotted the real-time data against the predictions, this is what you're seeing on the screen. And what you're seeing below from Christie, you're seeing those three, the circles are balloons, the squares are satellites, and the diamonds represent a little bit different kind of analysis that I won't go into here, but they're all real-time data, all right? And it's obviously what's happening. The predictions are way high and way hot. And the actual data is nowhere near those predictions. All right. So this is one example, but this was congressional testimony. There are other examples of this. Now, if this looks on your screen, if that looks too complicated, here was a simplified average that Christie did as part of that testimony. The red is the average of those 102. And then down below that, you're seeing the blue and the green, and I don't know if you call that a plum or purple or whatever it is. You can see the same thing. The real data is far below what the predictions were to be. Here's another image. This is also from Christie, from another part of the testimony. Look at what's happened. There's 68 models, CMIPs, that you're seeing from the year 1979 all the way up to 2020. And you can see they're all over the place, but they are all trending warm to the future. The black line that you're seeing, that heavy dark line, is the real-time data. Not only are those models running hot, but the real-time data is showing us that there's a cooling that's happening that the models don't account for. Now, why are we having the problems with the models? Well, what I'm going to say to you as a scientist, as someone who has experienced computer modeling in the past, again, it's not that the principle is bad. I believe we can model our atmosphere. The problem is, and the Earth and the oceans. The problem is that this is a dynamic that is so poorly understood that the models are incomplete. The models can only represent what we understand about the Earth and our relationship to the Earth. And there is so much more. There are so many spheres that we all know. There's the atmosphere. Well, there is the hydrosphere, there's the oceans, there's the lithosphere. That is the land. There's the cryosphere. And there's an interplay between all of these different spheres that is so poorly understood that it cannot be modeled in a way that can even tell us what has happened after it's already happened. Yet, this is the information that you and I are being asked to use, to trust, to change the way we live, to destroy our economy, to destroy a global economy, to destroy jobs, to prevent nations from achieving in their experience the benefits that we have achieved in ours. It is because of fossil fuels that we have lifted ourselves out of tremendous poverty. We use energy 6,000 places in our lives every day. It's just not about driving cars. This isn't just about airplanes. And most people don't even think about how that energy is used. Number one, then the people I talk to that say, oh, well, we will replace that with solar and wind and batteries. First of all, the 17 rare earth minerals that are required for all of our technology, solar panels, batteries, windmills, computers, cell phones, all of that. They're all based upon 17 rare earth minerals, and they are just that. They are not common in the Earth's crust. They are in essentially 2 to 3 large deposits. 2 of those are in nations that aren't our best friends, in China and Russia. And they are finite deposits. They are toxic to mine. In the case of cobalt used for the batteries coming out of DRC, Democratic Republic of China. The mining is happening through unregulated child labor, little kids barefoot standing knee deep in the water in these earthen mines. They're actually holes in the ground, digging through the mud with their bare hands for the ore that they put into a little pouch they wear around their waist. Then they send that to the adults. The adults aren't down there in that muck, it's the kids, to the adults on top, the adults that take this, they clean it up, they send it to China. China refines it, makes it into the materials that we need, and they sell it to us for batteries for our electric vehicles so that we feel, this is the virtue signaling, we feel that we're doing something good for the environment. The fossil fuel imprint that is required to refine and mine those rare earth minerals offsets the benefit by magnitudes, number one. Number two, they're toxic materials. Number three, at the end of their life cycle, what we're finding right now, solar panels showing up in, and batteries showing up in the landfills, those toxic materials are now seeping into the groundwater, into agricultural water, into rivers and streams, and people's homes and people's drinking water. Now, can we do something about that? Absolutely. The point is, we're not right now. And even the silicon itself, a lot of people believe that silicon just grows in the ground and you make a computer chip out of it. It takes very high heat to create a silicon chip, higher heat than can be accomplished through a solar panel or through a windmill. This takes fossil fuels to do that. So what I'm saying is, what we're being told is a solution. And I love solar panels. I've got 19 solar panels running the building and the studio where I am right now, where it makes sense. Geographically, where it makes sense. I love the idea. And I love the idea of electric vehicles where it makes sense. It's not one size fits all. We cannot place the future well-being of a global population on finite resources that are toxic on the beginning of their life cycle, toxic on the back end of the life cycle. They're expensive, they're not reliable, and they're not going to hold up through the climate changes that we're seeing right now. So I'm saying that because we're being asked to make those changes based on models like you're seeing on the screen right now that are it's not like they're off a little bit. They're predicting the apocalypse that I received through my email that AOC and Greta Thunberg are talking about. Those people are basing their passion upon the information of people they trust. That information, I used to say it was misinformation, disinformation, but now that we know it's true and we're still propagating information, we've got to call it a lie. This is a lie. It is a climate lie. All right. So let me tell you what Christie said in the paper regarding his findings at the House committee meeting or hearings. He said, quote, "The consensus of the models fails the test to match the real world observations by a significant margin." Okay, that's what we just said. The actual data fails to match what was predicted, and it's not by just a little bit. He goes on to say, as such, because this is happening, the average of the models is considered to be untruthful in representing the recent decades of climate variation and change, and thus would be inappropriate for use in predicting future changes in the climate or for related policy decisions. Now let that sink in. This isn't conspiracy. This isn't politically based. Here is a climate scientist telling you the data doesn't support the narrative. He's saying it'd be untruthful to represent what we've seen in those models, and that the models are inappropriate for use in predicting future changes, either in the climate or for the policy decisions. So here it is. How come we don't hear about this? This is part of the 5th generational warfare that I spoke about in another video. It's the warfare that begins in the mind and with our beliefs before it ever reaches the place where something kinetic is happening. There's a battle, many battles playing out. There's a battle for our body. There's a battle for our health. There's a battle for our beliefs, a battle for our thoughts. There's a battle for Earth. There's a battle for our divinity. And I talk about all of these in the videos that we have on this channel. That battle right now is being waged in our minds and in our hearts, what we believe to be true. And you're seeing this reflected in people all around us. And I wanted you to see, number one, because the climate change conferences are happening now. COP28 is happening now. Number two, we're going to have a year of people, of politicians. Some of them we may like more than others when it comes to climate, if they are telling you that we've got 12 years left. if they're telling you that we have to ban fossil fuels, what you know is they're either misinformed, they haven't taken the time to understand the policies that they're asking you to accept, or number two, they do understand it and they are part of something even more nefarious that I'll talk about in another video. One of those two things is happening. They're not alone. John Christie's not alone. Look at this. Dr. Judith Curry, she's a former chair of Earth and Atmospheric Sciences at Georgia Institute of Technology. This is a very prestigious university. Here's a link. You can see her entire statement. What she says is there is no climate emergency. We're being told that we've got to, the hysteria is just off the charts. Freeman Dyson, a physicist, British American theoretical physicist, very well known for in terms of the Nobel laureate and the principles that he's worked on. He says, I don't think there is any catastrophe. It's foolish to do anything spectacular, which is what we're being asked to do, to change an entire model of civilization in response to climate change. Now, nobody is discounting the fact that the climate is changing. And that's the point. As a geologist, I've been talking about climate change since 1979. It's my first year in the industry in Denver, Colorado, when I began working in the energy industry. Very well-known fact. Geologists know this. Climate change is a fact. Disingenuously, we're being told if we fight against it, that somehow we're going to change what's happening rather than adapting to the climate change. And I'm going to talk to you about where it's coming from here in just a moment. Adapting to it's only a problem if we're not prepared for the change. It's only a problem if we choose to live our lives and build our homes 10 feet from the edge of the ocean and have our vital power lines on spindly little sticks, the telephone poles that are vulnerable to high winds and to ice storms that come with climate change. It's only a problem if we continue to live the way we've always lived. We can adapt and prepare for and harden our power grids and do the things that are necessary to minimize the impact. And we're not doing that. We're being told falsely that all we have to do is give up an entire industry, way of life, and economy, and somehow everything's going to be okay. The evidence doesn't support it, just doesn't support it. All right, so I began, where's the information come from? I just gave you a couple of examples. The IPCC models are based upon computer models. Most of these are developed in the academic world. Good scientists, they just don't have all the information. We do not understand this, and I'm going to go into some information now and show you what it is we don't understand. So where's the information come from? I just covered that. It's all based, now think about this. This whole conversation, this whole COP28, the whole World Economic Forum push, the whole United Nations 17 Sustainable Development Goals, it's all based and predicated on the belief that carbon dioxide is bad. Number one, that it's bad for us. Number two, that an increase in carbon dioxide is a problem for us. Are we higher than we were 10 years ago? Yes. Are we higher than we were 20 years ago? Yes, we are. Is that a bad thing? Well, if we go back and look at history, it doesn't look to be a bad thing because Earth not only survived, Earth thrived. I'm going to show you that in those high levels of CO2. But again, what you're seeing here is that the CO2 levels that we have today, even though they're higher than they were 10 years, 20 years ago, they are nowhere near. We are on the low end of where carbon dioxide is historically on our planet. Now, what is driving the CO2? Here's a mind blower. I did an entire presentation on this. Check the link below in the comment section. And you can see the entire video. I've got it up here, absolutely no charge. Scientists have recently discovered there are processes underneath our feet, between the core and the mantle and the crust of the planet, that are driving climate change. All right, that does not fit the narrative. It's not what our presidential candidates want to talk about. It's not what high tech wants you to know. It's not what the World Economic Forum wants you to know. It's not what the United Nations wants you to know. It's what's happening. All right. And I do an entire video in much detail. I'm just going to highlight right now. The bottom line is that there are changes in the core that are driving changes in the mantle. The mantle is a hot molten material. There are places where it is being forced into the crust, as it does on a cyclic basis about every 13,000 years, 12 to 13,000 years. And there are reasons for that. As that warm magma is coming up near the surface under the crust, it is, and here's a beautiful model. What you're seeing right now on the right-hand side, these are called mantle plumes. These are computer models, they're computer imaging, modeling where this magma is coming from the mantle in a couple of places on Earth, and then it spreads and it's warming the Earth, it's warming the oceans. There it is right there. So what you see is it is happening under the Pacific Ocean, and it's happening under parts of Africa and into the Middle East. You would expect to see increased seismic activity where these things are happening, and that's exactly what you're seeing. Syria, Turkey, Pakistan, India, but you're also seeing it in the Pacific Ring of Fire. You're seeing it in the islands, all right, in the Pacific. So what is the implication, the climate implication? Now, I want you to look at the bottom of your screen. This isn't my theory. This isn't a conspiracy. Look at the bottom of the screen. This is climate.nasa.gov. NASA knows what I'm saying to you. Here's the quote: 90% of global warming is occurring in the ocean, causing the water's internal heat to increase since modern record keeping began in 1955. All right. What's the big deal? What does that mean? If you remember your high school physics, cold water holds more gas. Carbon dioxide is a gas. The oceans of our planet are the biggest, it's called a sink, a carbon dioxide sink, S-I-N-K, or a sponge or an absorber of carbon dioxide. And they continue to. The oceans are absorbing a lot of carbon dioxide, as are the forests. That's going to be important in a minute. When the oceans are cooler, they hold more carbon dioxide. When the oceans warm, guess what happens? They will hold less gas. Where does that gas go? It's emitted into the atmosphere. It's exactly what's happened. Now, 340 gigatons of CO2 annually are coming from the ocean, as opposed to 35 to maybe 40 gigatons from industry. All right, so the oceans are where most of the CO2 is coming from. The oceans are warming, but look at this. They're warming from the bottom up. Glaciers are melting from the bottom up. They're melting from underneath. That would not be the case if the warming was from the atmosphere. I'm not saying to you anything that scientists don't already know. These scientists just don't have a platform, and they are beholden, in many cases, in academics, they're beholden to funding sources, and they can't talk about stuff like this. So this is NASA telling us 90%. Yeah, are we contributing a little bit? But it's not causing the climate change. We are not the sole source of CO2. We're not the sole source of greenhouse gases. That is a statement that was made by one of the participants at the COP28 in a television interview. He said, we are the source of the greenhouse gases. Not true. Fossil fuels, he said, are the source. Not true. All right, so this is where this is coming from. Now, I'm just going to do this again. I'm going to do this very quickly. Is carbon dioxide bad for us? Well, let's take a look at the past. Triassic period in geologic history is a very specific mark in time. Carbon dioxide was high, 2,000 parts per million. Right now, it's only 417 parts per million. Earth didn't die. Forests were green. It was warm on Earth. How warm? Between 122 and 140 degrees Fahrenheit was the global temperature. These are like Dubai temperatures as a global average. Uncomfortable for some people, but certainly not the end of the world. Now look at this. Jurassic period, and we've all heard of this because of the movies, CO2 dropped to 1,000 parts per million. And again, we're at 417. 1,000 parts per million, the average global temperature, not bad, 80 degrees, 80.6, 81 degrees during the day, 59 degrees at night. Those are nice temperatures. With 1,000 parts per million, much more than we've got right now. But then look at this. During the Cretaceous period, CO2 jumped back up to 2,000 parts per million. It didn't drive the temperatures up. Look at this. Global average temperatures, 82 degrees Fahrenheit. It's actually 2 degrees warmer, and 52 degrees Fahrenheit at night. There is not a direct correlation between carbon dioxide and temperatures. There are other factors, and those factors are not incorporated into the climate models that are being used right now. By the way, where you see in the Jurassic and Cretaceous, those higher levels of carbon dioxide, the forests were deep, dense, green, abundant sea life, abundant land life. This is diversity of life that was thriving because CO2 is food for the plants. It's food for the forests. Now, United Nations, World Economic Forum, they have given us very specific targets. Now, I'm speaking quickly because this is a summary to more detail in the other videos. They're giving us targets they want to meet. 2021 carbon dioxide level is 414.7 parts per million. The United Nations is using the year 2010 as the baseline, all right, at 390 parts per million. All right, and what the UN wants to do, the goal is a 45% reduction from 2010 levels, all right? 2010, 390 parts per million. 45% reduction in that would be 214.5 parts per million. If that sounds low to you, you're right on. That is dangerously low. You don't want our planet to drop to 214.5 parts per million. Let me show you why. This is from a peer-reviewed paper published in the journal Nature. This is Nature Communications, 2019, so it's fairly recent. If we were to reach those climate goals, when was the last time we saw them on planet Earth? It was during a time called the Pleistocene epoch. All right. This is a direct quote from that paper. The study shows that for the entire Pleistocene era, CO2 concentrations averaged 250 parts per million. They averaged 250. Look at this. The UN wants us to go all the way down to 214. Well, what was Earth like at 250 parts per million during the Pleistocene? Well, check this out. The average CO2, the average temperature, the average ice, and what it did to life. During the Pleistocene, the average 250 parts per million. Today, it's 417 parts per million. The average temperature was 46 degrees Fahrenheit. Today, it's 57. So the average global temperature would cool by 11 degrees. The ice coverage, this is a big deal for agriculture, for when we plant, when we harvest, when seasons begin, when seasons end, when the rain happens, when the rain stops, when the snows come, when the snows stop. The ice coverage during the Pleistocene, look at this, 8% of the Earth and 25% of all the land were covered in ice, primarily Northern Europe, North America, certainly up through Canada. Today, we're nowhere near that. Only 3% of the Earth and only 11% of the land is covered in ice. Do you want to go back where the global temperature is 46 degrees average, where 25% of our land is covered in ice? And look at this. During the Pleistocene, there was a loss of forests. Forests died because the food for the forest, the CO2, was low, and the ice covered the forest. The forest couldn't live under the ice. There was an extinction of large mammals. At least 32 species died over the course of a couple of thousand years. What's NASA saying right now, in the little bit of warming that we've had, the little warming and the little bump in CO2 that we've had in the last 20 years, NASA says Earth is now greener now than it was 20 years ago. Earth's forests are thriving. And this is important because the forests are absorbing excess carbon dioxide that is produced through volcanoes, through natural events, as well as through human industry. We need those forests. If we go back to 46 degrees Fahrenheit, average temperature, 25% of the landmass covered in ice, we lose forests, we lose the ability to absorb that CO2. I'm not even talking about the sun and the solar minimum. I'm not even talking about the Milankovitch cycles that play into this, all contributing to these shifts in the climate. So if we were to meet those UN, United Nations, World Economic Forum goals, we would see an Earth like we have not seen since the Pleistocene. So now you got to ask the question, who benefits from that? Who benefits from a planet that has less forest, is colder, has fewer forms of life, and it's going to impact human life, human migration? We're going to lose people. Who benefits from a lower human population and a lower animal population, a colder climate with fewer forests? The answer to that question is beyond the scope of what I can do. Well, in this, I wanted this to be concise. I wanted you to see where the UN data is coming from, but I'll give you the answer in a nutshell. It's not us. This isn't good for us. We don't benefit from this. And you have to ask yourself, who does? That is a conversation for an entire video. The climate hysteria that we're seeing right now, who benefits from that? The well-intentioned people that are perpetuating what we now have to call lies. We have to call them lies because the data is there. The scientific community knows that the models are running hot, and yet they are still attempting to collapse an entire industry based on fossil fuels that are arguably contributing to higher levels of CO2. If you think that's a problem, then you have to ask, why have we not brought forward the technologies that we've had for over 70 years that the industries today simply don't want on the market because they can't compete with it? There's an economic principle going on here. This also ties into what is being called disclosure. You know, disclosure, we've talked about in other videos, a lot of people are talking about the disclosure of our relationship to life beyond this world. If we have vehicles that have come from somewhere else, either another planet or in a future time, that are traveling back in time, if we have that, and we're being told we do, and if we have the beings inside those vehicles, and we're being told that we do, then we also have to have something else. Those vehicles didn't get here on a Ford V8 internal combustion engine. They didn't get here on what was powering your dad's Chevy Camaro, you know, those eight cylinders. They are moving on a form of energy that not only is a form of propulsion, but is a source of energy that could revolutionize our planet. Not just revolutionize, but free humankind from the bondage and the shackles of the tyranny that has come from a finite source of energy that we've been using for 150 years. All right. If we want to phase out those fossil fuels, if we really want that, and I'm not sure that we do, I think we can keep those fossil fuels and incorporate the new forms of energy as well, and have them very harmoniously giving us options, because one size can't fit all. One size can't fit all on a planet as geographically as diverse, as climatologically as diverse, as ethnically as diverse. We have different needs, different dreams, different goals, different desires, different ways of living, and there's room for all of it without the hysteria of frightening people and keeping people in fear. So once again, we have to ask ourselves the question, the choices we're making, are we making the choices based on the love of what we know is possible in our lives, or have we succumbed to the fear of what happens if we don't make those choices? There's a fifth generational warfare that's being directed at you and me so that we do the former, so that we make our choices based upon the fear that is being perpetuated through climate science that simply is not supported by the data.